screen. Okay, can I just, oops. Can I just check that's coming through okay?
Yeah.
Great, and I'll just quickly put in the chat if I can. Where's the chat gone? Here we go, chat. A link to the models. So yes, I was going to talk today about sort of how to develop and work with these MVLV distribution network models. There's some models which we presented at PowerTech this summer and we developed last summer. And what I was going to talk about, so firstly, because it's there's everyone here, I was going to just do a sort of short couple of slides just on the motivation for when you want to work with these sort of MVLV network models. So sort of why might you want to work with them and practicalities of actually working with them, what sort of analysis you might do. But the sort of meat of the presentation, I'll be sort of thinking about how to, if you want to actually go and work with these models, if you like, how could you go in, work with those models, change them, do things to them, how to sort of run power flows and pull out useful numbers. And so I was going to talk through sort of how I've structured those models to sort of try and make it sort of scalable and usable for people working with them. And if you wanted to make changes to the models, sort of the general workflow, some notes about how to validate and bits and pieces like that. There are a few things which I won't talk about. So I won't talk about how to convert from MapPower to OpenDSS or these sort of between different file formats, which is something that I had to do as part of this. Won't talk about, again, in the PowerTech paper, we talked about splicing the LV distribution network models to reduce the number of nodes so that these models actually, so that you can run these models, because if you, it turns out you can sort of reduce the size of the models by about a factor of 5, which makes a huge amount of difference. I also won't talk about, I'll be focusing on these sort of European style networks. I won't talk about the sort of United States style networks. So there are these massive networks that have come out of the guys at NREL. So I don't know if people are good at maps, you'd recognize this as the Bay Area. And they've built this absolutely humongous sort of synthetic network for the whole Bay Area that I forget how many nodes it's got, but it's absolutely enormous. So we're not that scale with sort of 100,000 nodes is about as big as we're getting, which is still much bigger than you get in the IEEE test cases, but it's not quite on that scale. So I've put here that net zero is a motivator because net zero is a motivator for everything, I suppose. But sort of more generally in this space, the reason that this is starting to become an interesting problem is net zero and the sort of development towards much more active distribution networks. So if you have consumers which are responding to market signals, which are all higher than the level of your low voltage network or medium voltage network, then everyone's going to be doing things at the same time. And it could be responding to carbon intensity, which sort of seems to be forever coming up, or it could be flexibility markets, which are sort of, I think, if not all DNOs, most DNOs are now implementing smart tariffs. Again, that's nothing to do with the distribution network, but everyone in the whole service area has the same thing, or active buildings doing sort of similar things. So this increases the coupling between demands on a much wider scale than has existed in the past. I mean, everyone gets home at the same time, but there's not an actual beyond that to sort of control signal that says, you know, you should charge your electric vehicle at, okay, there's economy 7, I suppose, but these sorts of things are becoming much more common. On top of that, you have this sort of bidirectional power flows. People have been thinking about this for a long time, but it means that, as we'll sort of see in a second, you get a different answer to thinking about what the worst case might be in a distribution network. And then the final thing is that if we're going from this sort of DNO to DSO, then you have potentially much more of this sort of optimal power flow type things within distribution networks. So the DSO can actively say you need to turn off or you need to turn off and so on and so forth. So the particular networks that we developed sort of had three features that we wanted to tick off. So we wanted to be able to look at sort of scalability issues for smart grid problems. So it works on a single low voltage network. What if everyone in the whole neighborhood is doing the same thing? We wanted to include this medium voltage coupling, just the fact that power flows on the medium voltage network will be interacting with other, everyone on the same feeder will be, its voltage will be changing at the same time. And we wanted to also include, as much as possible, low voltage diversity. So having a whole load of different types of template networks going into these models. And I would say that when you're thinking about it, just because we've developed these models doesn't mean that you have to use them. Make sure that you use them for the right thing. So if what you care about is service cables, then you shouldn't be modeling a medium voltage, low voltage network. You should just be modeling an individual house. The sort of problems that come up with the medium voltage, low voltage network is this sort of thermal problems at the primary substation. Now, you probably don't actually need the physical network to do that. So long as it's not a really, really heavily loaded network, you can probably just assume that the losses are a couple of % and then just add up all of the loads that are downstream of the substation. The sort of where it really comes in is probably these sort of power quality things. So thinking about voltage unbalance and thinking about steady state voltage constraints. They're the sort of the real sort of use cases. And there are other things you can think about, but in this sort of event tool, that's what we'll be focusing on. We'll be focusing on the thermal and the steady state voltage constraints. How difficult is it? Well, if you want to just run a power flow, if anyone has OpenDSS on their computer, you can run these in a couple of seconds. So I forgot to put the table in here of how big these are, but they're sort of, as I say, 100,000 nodes, sort of 20,000 customers. And in our experience, the solution time approximately grows sort of linearly. And I don't have a graph that shows exactly this thing, but if you look at, it solves by, the way that this is solved is it has solves through 4 voltages through the admittance matrix. So it's this sort of sparse matrix inversion. And that's basically what we did in this recent paper. I mean, it's slightly different, but you can see that this implicit one is similar to what OpenDSS does. And that's sort of, you can see that this is basically a linear fit. So it's growing something with n number of nodes. For a linear power flow, if you just have voltages as a matrix multiplied by power injections plus a constant, then you go with number of nodes squared. So if you want to run linear power flow in that sort of simplest setup, then it's sort of getting quite a bit more tricky as things get bigger. So for example, for 100,000 nodes, if you look at the size of the matrix, you need like 100 gigabytes plus to sort of work with those sorts of problems at 100,000, unless you do something different. And then optimal power flow, I haven't done so much on. These two I've done quite a bit on. So I'm interested to find out more about how people find sort of how the OPF problems actually scale. So that's sort of but it will depend on how you formulate the problem. In terms of actually sort of, if you have some MV-LV system, so this here is the UK generic distribution system underground circuit at HV, or so where the UK, in UK parlance, HV, high voltage, would be called MV on a sort of European scale. So when it says MV-LV in the UK, it would be HV-LV, I suppose. And what you could do is if you want to model a low voltage feeder, let's say this 1101, then you could run the power flow with all of the loads at a maximum point, and then just assume that all of the analysis that you run is with the voltage at that lowest point. The problem comes in when you have active systems, basically, and you've got this bidirectional power flow. So if you just do that, you've got this sort of very pessimistic view of what the voltage would be at that given node, potentially. So other things you can do lump load approximations. So in these cases, you don't just run a single snapshot and then do all the analysis on top of that. You keep all of the detail in terms of the time series of what the loads are doing, but you lump all of the loads that are downstream of a given point into that point, and then you just model maybe 1 or 2 networks in detail. So here we're modeling this 1101 and 1151 in a lot of detail, and all of these other sort of turquoise and yellow dots that you can see. These are just being modeled by aggregating all of the loads that are beneath that point. And that's quite close to what people do in practice. Often people don't even bother modeling low voltage, which is fine, depending on what question you're asking. But this is what we've implemented in the event tool. So you can put up, I think it's up to 5 networks that you can model in detail around the distribution network. And then if the sort of, you can do a lot more if you want to do this linear power flow and optimal power flow stuff. So because the distribution network has this tree structure, the sort of coupling between the voltages, there's sort of a structure in there. So in this sort of paper that we got accepted in the summer, we implemented what we called this block sparse plus low rank formulation, which is a linear formulation, which we show in the paper is much more efficient than just having this sort of massive n squared nodes, which becomes infeasible, as I say, at these sort of big network sizes. So there's lots of things that you can do, which are sort of interesting things for people to work on going forward. So that's my sort of brief introduction to the system. So for the rest of this, as I say, I'll sort of talk about building these systems, and if you wanted to tweak them, how you might tweak them. And as I say, I've put a link in the chat, so you can sort of, I've put some things in here so that you can perhaps follow along if you wanted to. So as I mentioned, the MV models are based on the UK generic distribution system, and at each load, as we had in that previous figure, we put on the bottom one of these low voltage network solutions, LV network models. And so this is what the UK GDS networks look like. So there's 75 loads in this underground sort of urban model. And there's, I think, something like 200 in this underground overhead model. Now, one of the limitations of what we developed in that PowerTech paper is that you can see that on this network, you kind of have these kind of look similar-ish to this. You've got quite a few relatively big loads that's sort of a couple of hundred kVA. We have a whole load of these loads here, which are much smaller, sort of only, you know, less than 100 kVA. We don't have at the moment good models for, or to our knowledge, there aren't good models that are just sort of out there that you can go and stick on the end of these. So we sort of, in the original models, we sort of cheat slightly in that we take those low voltage networks and we pull out individual feeders, which are then small, that we then stick onto these loads that have very low power levels. In practice, if you look at how these are built in reality, these are more likely to be possibly sort of single phase transformers with just 1 or 2 customers. And so the models that we have there aren't so great. The models we do have are much more based, as I say, this low voltage network solutions, which is come out of Manchester, and they've got these network models, which are much more sort of suburban networks. So this underground network model is pretty reasonable. We know that this could be improved. Anyway, though, so that's sort of what motivated this tutorial, I suppose, was how could someone go and change these to put rural networks in this sort of in one of these models if they wanted to. So because the networks has this medium voltage, low voltage, and then on here, the different colors are representing the different feeders of the low voltage network. So you can see this one, there's sort of these four colors. For this network 7, I think there's 7 or 8 of them, if you count carefully. So because we have that medium voltage, low voltage, and then feeder, what we can do is we can sort of build that into the tree structure of the actual network model. And this is a common thing. So I think I pointed you to mentioned that 1 million node network at the beginning from NREL. So if you go and download those, that's structured in this. So they have the lower voltages going into the higher voltages going into the sort of subtransmission. So in what we have this master medium voltage network file, which points to sort of basic information, a sort of whole load of basic information files. I'll show you these in a sec. There's a particular file that we use to tweak the network loads. So because what we're doing is we're putting a network on this load, for example, we append the network and then we disable the load. Because we've still got it in the model, right? We haven't just deleted that line. It means that once the model is built, you can very easily go and re-enable that original load that was there without having to find it from somewhere else. So it's all sort of still there. So instead of deleting that, we just disable it. So that's what this particular part is. And then we have another file which then points to all of the sort of lower level. I've called them slave networks because that's just the terminology that I used. And so this will match up with what's in the files. Maybe lower level might have been perhaps more suitable, but that's what I've called them. So I'll refer to them for that for now. So that then defines the sort of high level information about the low voltage network, which then points finally to these low voltage feeders. And then we have a whole bunch of feeders here. So 1 to 1N, if there are N feeders for this network. And then you have a whole bunch of low voltage networks up to M, and then you have a whole bunch of feeders for those. What does that look like in practice? So for those of us who have clicked on that and downloaded the models from GitHub, so when you download it, you won't have this unzipped file. You have to unzip, and if you go into that file, you have master. So the master is sort of the main. That's the sort of first thing that's where you run these models. You have generators, lines, loads, reg controls for the regulator controls, the substation, and transformers. So they're the sort of basic circuit information. You then have this LUDS edit, as in loads edit, editing the load. So that's where we disable all of the loads if you go into that. And then we have this redirect LV networks. So that's what points to all of those sort of slave network files that I mentioned. So that points through this LV networks directory into all of these. So there's these 75 networks for the underground model, as I mentioned. So it points through those into through that network. We have these 4 feeders as it happens. This directs to this slave network DSS file, which in turn points to the information in the feeder. So that's sort of this tree structure. So in theory, it's built in such a way that you can sort of work through and get the levels. So I won't talk through all of these. I put this slide in for anyone who wants to study it afterwards. You can map what I sort of mentioned previously onto the exact load files. Now, those just to sort of highlight those sort of what I call the slave network files. So there, if you just want to run an OpenDSS file, then you run it, and the way that it works is it defines a circuit, it defines the voltage source, defines your transformers, then these redirect, that means load in another file. So this is loading in some line codes, some lines, some loads, and it's doing that for all of those 4 feeders. You then define various bits that you would need to run the network. So there's these 2 commands that you have to call as it happens. And then you solve. So this file here, if you run this, will define the network and run the network. And then the exclamation mark is the comment mark for OpenDSS. So these here are just commenting out plot commands, but you can uncomment them if you want to plot various things. In the slave network, we strip out all of that information that we don't use. So here I don't know if people have seen a diff before, but I've taken the diff of these 2. So where this negative is, that's what's been taken out. So you can see we've taken out all of that, and we've just got the redirects for all of the definitions of the particular sort of data files that are in here. Now, a thing which I implemented, which isn't in those NREL networks that I mentioned before, is that I've got this sort of schema or naming convention to keep track of what's where. And I implemented it, and it's been extremely useful. So and I've meant to put it in here because it means that if you keep to this form, then you'd be able to just plug in a different network and it would work. So I've got this sort of set of characters which will define, which we put on I'll show you again in a sec. We sort of put at the beginning of names of things, so names of buses or names of loads, which means that you can work out where it is in the network. So the form is 1_, then the load number, underscore the LV network type. So from the low voltage network solutions, there's 25 networks. So that this is numbered 1 to 25. And then from that, the low voltage feeder number. I think if I was doing this again, there'd be another underscore here to make it a bit easier, but this is what I did. And it does work. So for example, if you get this code, again, I'll show you one in a sec, then you can see that the load number is 1104, LV network type 23, and feeder number 2. This means that, yeah, it's unique and identifiable. And this is useful. So again, this is another one of these diffs. So I've taken from those low voltage network solution models, the original load file and what it looks like after I've sort of put this schema in. So all of the feeders of those on the networks as they're defined, it just goes load 1, 2, 3, 4, 5, 6, 7, 8. And that's problematic in OpenDSS because you need elements to have a unique name. So if you were to just try and load these in, then you would say this is a problem, you need a unique name. So we put that naming schema, naming convention to enable us to have unique names. So we go from load 1 to load, and then this thing here is the schema, and then it's _1 to all the way up to sort of 54. And it's the same for the bus here as well. As it happens, so this daily equals shape I've taken out. So that's why that's purple here, is because it's been taken out. And that is for time series analysis. So we didn't need that. So that's why that's not there. So in this case, the schema is 1, 11, 19, 194. So it's load 11, 19 being replaced with LV network 19. And these loads are on feeder 4. So we've sort of gone through that tree from the beginning to the end. So if you wanted to add a rural low voltage network to an existing model, so I'm going to assume that you already have the MV network model, which you could just take from this GitHub. And then you've already got some low voltage network model, which you're happy with that it works. So the first thing that you would do is you want to define that sort of schema, that naming convention. So if we pick out, we want to move a load called 1033 with an LV network 30, and there's just one feeder, then this is the schema. You would then build you would then take your low voltage network and then build a script or write a script or something to convert the loads, lines, and if there's generators or anything like that, to have this sort of form prepended onto the name and the bus names and so on and so forth. And then build this sort of pointer file, which doesn't run it doesn't build its own OpenDSS model. It just loads in the information to back up to that big master file. And you need to make sure that when you do that, that you update the substation transformer to have the bus that matches what it ought to be on the medium voltage network. So if you go into the files, you can sort of see that. And then finally, you would then go and do the connection. So you would just put an extra line into the redirect OpenDSS file and update that loads edit file to disable the load which you're replacing. And then you'd run it to validate it. So this is a sort of nice example of that schema. So this here is the voltages for each of the 75 networks in the HV underground network. And the way that I've gotten these voltages is that I've solved the power flow solution to get the voltage magnitudes, and then they come out as a big long vector which has the names of all of the buses. So you can loop through those names of the buses, pick out LV circuit number 0, which might be load 1101, and just pull out the voltages for that particular network. And you can do that then for all of the LV networks because you know by the name of the bus where it is in the network. So that's sort of super duper useful, and I use all the time when I'm working with these models. But more generally, you just need to run these things to validate that what you want it to do is doing. So this is again just from the PowerTech paper. Run and check that the medium voltages are about what you'd expect them to be in the low voltages as well, and that you've not got because you just need to check that the sort of electrical connections that you've made in the model, as it were, have passed through and are actually being solved. So to conclude, with this sort of increased data availability, these sort of business models, low carbon technologies, and so on and so forth, distribution networks are becoming, a really interesting place to be working. And much more money goes into distribution networks than goes into transmission because it's so much more extensive. So if you can even make a small benefit difference, then it makes a big difference across the UK. Using this sort of structured approach, which I've talked about, exposes those sort of methods of doing efficient analysis because we have this sort of tree structure that exists in those networks. And this schema thing, as I say, it was just before this talk, I thought I'd go and have a look and see if they do something similar in the NREL ones, and I don't think that they do. So as I say, if you were to work with these, I would definitely try and keep something like that. And if you're working with these particular models, if you stick with this one, then hopefully it will mean that you've got a consistent model that's sort of keeps this high usability. In terms of future work, as I say, I've mentioned trying to do these non-suburban low voltage networks, thinking more about where industrial and commercial loads might be, thinking about validation using much more detailed smart meter voltage data and so on. Algorithmic development, so there's all these things that we've mentioned, TSO, DSO, peer-to-peer, building services and so on, which are all relevant. They're all doing sort of something similar to what we've proposed here. And then, of course, Miriam's introduced the event tool briefly, but that'll, I think that